Today we will learn about nuclear stability. Okay, so there is a curve that is in y-axis we have binding energy per nucleon, and in x-axis we have mass number. So we will explain this figure and we will see how this figure actually describes nuclear stability. Okay, so in a nucleus we have some protons and then we have some neutrons. Now the thing is, the protons all are positively charged, right? So these protons have, since they are all positive charged, so they repel each other, so they have a strong repulsion force. So in the nucleus, all these protons were supposed to repel each other, but it is not the ideal case, right? Because if that happened, nucleus wouldn't exist. So what happens is another force comes into action and they force the protons to stay together in the nucleus, and we call it strong nuclear force. But the problem with this strong nuclear force is its range is very short, that is 10 to the power minus 15 meter, or that is 1 femtometer. Okay, so what happens is, as the mass number increases, the radius of the nucleus also increases, and the equation is like this. So we can see that when A increases, the radius also increases. So for bigger nucleuses, when the mass number gets heavier, their radius is also gets bigger. Since the radius gets bigger, the nuclear size gets bigger, and as we said that the strong nuclear force is very short ranged, it cannot keep up with the repulsion force throughout the nucleus, since the nucleus has become too large. So the impact of the strong nuclear force become weaker on the whole nucleus. Now you can see, now you can tell that in the nucleus there are protons, neutrons, they are everywhere. It's not like the strong nuclear force is acting from the center, so its control over the edges become weaker, right? You are fair to ask that question, but the thing is, um, strong nuclear force doesn't act from the center like gravity or Coulomb force. That is right, but instead, it works more like a contact interaction. So suppose this is a big nucleus and this is a strong small nucleus, and suppose let's do we have two nucleons contacted here and we have two nucleus contacted here. Okay, now strong nuclear force comes into action when two nucleons are connected, are in contact. Only then. So here in this pair they are connected, so they have a strong nuclear force, so their impact in this area exists, but in the bigger nucleus there's their impact in this area exists very weakly. Okay, so that is the case in a larger nucleus. The strong nuclear force of one point impacts weakly on the other edges, while repulsion force is stronger. You see the repulsion force is stronger here in the every cases. Like the repulsion force of here also strongly prevails here. They have a much stronger impact, but the strong nuclear force cannot keep up with this strong force that is on the further edges from the strong nuclear force uh, source. So this is why the strong nuclear force cannot keep up with the increasing repulsion force. because the nuclear size gets bigger. Okay, so this is the thing that in when the mass number increases, the nucleus size also gets bigger, and it becomes unstable. This is the reason why in heavier nucleus, the stability is less. Now, if you think about from binding energy point of view, so this strong nuclear force comes from mass defects, right? So we know if this is mass defects. So mass defects comes, uh, uh, it becomes mc squared to provide the binding energy, and this binding energy is basically the strong nuclear force here. So suppose we have two atoms. One has small nucleus, one have large nucleus, and say they both have a similar binding energy. For example, they have 100 electron of binding energy. Now the thing is, suppose we have only two nucleons here, and suppose we have uh, four nucleons here. Now this binding energy will be shared among the nucleons. So for each nucleons, the binding energy will be 50 electrovolts, and here it will be 25 electrovolts. So in which case the stability of the nucleus will be stronger. Obviously here, because if you want to destabilize, or if you want to take one nucleon from the nucleus, you need to break 50 electrovolts. You have to fight against 50 electrovolts. And here you have to fight against 25 electrovolts. So fighting against 50 electrovolts will be harder, right? So the stability of the nucleus depends on the binding energy, that is true, but it is more likely binding energy per nucleon. Okay, not only binding energy but also binding energy per nucleon. Okay, so in the graph we can see that binding energy per nucleon is maxed for iron. Okay, so this is the most stable position a nucleus can have, and the right area, the right part of this region is here fission fission reaction takes place, and here fusion reactions takes place. And why these nuclei take part in fission, and why this nuclei takes part in fusion, we will know the explanation in next video.